So I think in the last class we stopped here and we said the question of why do parts fail enabled us understand the mechanical behavior of materials and their life cycle, improvement of the life cycle of the products in the long run, right. So, all of you are familiar with the concept of Mohr circle. I am assuming that all of you are familiar with the concept of Mohr circle, right. If you are not, you have seen this or you have heard of this in your strength of materials class or mechanics of materials class. Please go back and refresh your memory, right. So, Mohr circle is a very powerful way of representing stress state in a material graphically, and we know how to represent the stress state of in a material or at a point if the system is 2-dimensional, and you can also represent a 3-dimensional state of stress at a point using Mohr circle, right. You probably have done for 2D state of stress, but you can also do the same thing for 3D state of stress. So, the figure here on the left hand side is actually for a plane stress or plane strain problem. So, plane stress case, and here you can say this it's a 2D state, and this is you can actually say 3D, wherein you have 3 principal stresses sigma 1, sigma 2 and sigma 3. Okay. So, here on the left hand side this is the Mohr circle for uniaxial tension test, right. When you are doing uniaxial tension test, what is the state of it is uniaxial, that means there is only one normal stress, right. So, that is your principal stress. Why is that your principal stress? Because in that plane there is no shear stress that you are applying, you are only pulling like that, isn't it. So, that is one principal stress, and the other two principal stresses will be 0 because it is a uniaxial loading scenario. And if you would take that and then draw the Mohr circle, that is how it looks like, and it clearly shows you that there are planes along which, although the applied stress is uniaxial in nature, there are planes along which you also may have shear stress, right. So, each and every point on this Mohr circle's boundary is representing the state of stress at some other planes, right. So, you have for instance this plane at an angle of 45 degree to the direction of application of your uniaxial load having a maximum shear stress, right. You also have seen why when you are applying a uniaxial tension test your failure or yielding happens along 45 degree plane, right. That is what something that you have observed in your experiments, the shear bands you probably have seen, and that is because you have shear stress to be maximum at 45 degree plane, and that represents what? If you have maximum shear stress, it is possible or it is probable that along that plane you will have initiation of plastic deformation, because plastic deformation is primarily due to the slip of atom planes which is caused by shear stress. Okay. And now on the right hand side you have Mohr circle for the case of pure shear or torsion, right. So, when you have pure shear, if you are applying torsional loading, then you know that the principal stress sigma 1 is equal to negative of sigma 3, and let us say this is also a plane problem. So, sigma 2 there is no sigma 2, sigma 1 is equal to negative of sigma 3, and that is when you see that these are same but in the opposite direction, and then you can draw the Mohr circle, right. And in both the cases, whether you are applying uniaxial tension or shear, your yielding happens only because of the shear stress. Whether you apply pure normal stress or pure shear stress, your failure is only due to shear. Here when we say failure, we actually mean plastic deformation, right, yielding of the material. Is that clear? So, that is something that I have mentioned, right. In the last class when we have discussed, there are different ways that one can define failure, and as far as ductile material design is concerned, we will restrict the definition of failure to the yielding of the material. We really do not have to completely break the specimen, because the moment the yielding happens there is some permanent deformation set into the material, and because of the permanent deformation the functionality for which it is designed might not be met, and that itself can be considered as failure. So, whenever we are designing components made of ductile materials, the failure criterion is based on the yield strength of the material. But for brittle materials, there is no possible yielding that can be observed, and usually for brittle materials, you will consider permanent fracture or breakage as the failure of the material, right. All right. So, in a static tensile test, in general, ductile materials are limited by their shear strength and brittle materials are limited by their normal strength, because they fracture by normal strength. So, obviously, the failure mechanism is different in both these materials, and hence you cannot have same theory explaining the failure of both the materials, right, because the phenomena itself, the mechanism itself is different. So, one kind of failure theory cannot explain failure of all kinds of materials. So, you basically need to have two classes of failure theories, at least one for ductile materials, class of ductile materials, and another for a class of brittle materials. Okay, that is the key thing to understand, why we cannot have same failure theory for both ductile and brittle material, because the mechanisms themselves are different and the way that we are characterizing failure itself is different in both the materials. Okay. But before we actually go about prescribing a failure theory, we need to understand what do we mean by failure. So, that is what something that we have discussed. In the case of ductile materials, what do we mean by failure? In the case of brittle materials, what do we mean by failure? Okay. So, how do you consider a material to be ductile material? What is the limit? Do you have materials with, can you say in black and white, this is ductile material and this is brittle material? Is there no material which are somewhere in between, right? It is always possible, right? And hence you need to have some quantification to classify a given material as a ductile material or a brittle material. So, the classification is basically percentage elongation. If the percentage elongation up to fracture is greater than 5%, that is when you call something as a ductile material. But typically, most of the ductile materials will have almost 10%, but for definition or when you want to classify a material to be ductile, so you will see the percentage elongation until fracture is more than 5%, and then that is when you say that okay, this is what I am going to consider as a ductile material. If it is less than that, then you will consider that as a brittle material. Okay. All right, I think this is something that we already discussed. A component may be considered failed if it yields and deforms sufficiently large, leading to improper functioning. That is the key. The definition of failure for us as engineers is not necessarily breakage of the material, but the moment the component ceases to deliver the function for which it is designed, that itself is a consideration for failure of the component for us. Okay. So, sometimes the component might actually fail by fracture, it is possible, for instance brittle materials. So, both are considered as failures, but it depends on the mechanisms are different. In addition, so we are only talking about failure, whether it is failing by slip or permanent deformation or breakage, but we have not paid attention to the kind of loading. Is the loading time independent or time dependent? That means as a function of time, is my loading changing or not? As a function of time, if the applied load does not change, then such a scenario is called static loading scenario. If the load changes as a function of time, then such a scenario is called dynamic loading. So, the failure phenomena actually depends on whether you have your load changing as a function of time or not, and hence you also need to pay attention to the nature of the loading, whether it is static or dynamic. So, in this module, the first module, we will be focusing on static failure theories. That means there is no change of load as a function of time. The function of time, as a function of time, if the load changes, and then we will have to come up with a new way of deriving the failure theories, and that we will do in the next module. That is when we will look at fatigue failure of materials. But in this module, we will restrict ourselves to static failure theories. And so, as we have already mentioned several times, so ductile materials fail by fracture if loaded beyond ultimate tensile strength. Until then they won't fail by fracture, but we will not, when we are designing, we will not go up to there. We will only consider, we consider them to be failed when they yield under static loading. And why do we, for ductile materials it is important, because the yield strength and ultimate strength are not the same, right. The yield strength, suppose for instance for a mild steel, your yield strength is about 200 MPa, 210 or 200 MPa, right, whereas the ultimate strength can be up to 350 to 400 MPa. So, there is actually a reasonable difference between the yield strength and the ultimate strength. Whereas for brittle materials, it is not possible to distinguish these two things. That is why we cannot use yielding as a phenomena. Whereas for ductile materials, it better be yield as a phenomena for failure. Okay. All right. Now, we need to establish the need for failure theory. Why do we need to come up with a failure theory in the first place? So, here you have three scenarios. You see the first case. So, here we are considering a material which is elastic perfectly plastic. So, elastic perfectly plastic material will not have hardening, right. That is what we have discussed in the previous module when we have looked at mechanical behavior of materials. So, this is a typical elastic perfectly plastic material, and now in the first figure, this figure, we are applying uniaxial load, and you observe that the material yields at sigma naught, that is sigma naught is your yield strength, sigma y is not yield strength, sigma y is the load applied in the y direction, the stress in that direction, right. Sigma naught is your material property. So, what you have observed is when you are loading the specimen uniaxially, you observe that the material is yielding at sigma y equal to sigma naught. That means you need to apply your sigma y until it becomes equal to sigma naught, and that is when you see that there is a flow of the material. That means that is where the plastic deformation has initiated. Now, you do another experiment wherein this load is there, but laterally you apply another stress, that is sigma x, but that is compressive. Okay, you are pulling one guy in this direction, at the same time you are applying a lateral normal stress, but that is in compression. Then if you observe and you see that the material starts yielding when your applied stress is 1/2 of the yield strength in the previous case. So, let us say my sigma naught equal to 200 MPa. In this case, sigma y equal to 200 MPa is the onset of yield. Here what we are doing, I am applying sigma y in this direction, sigma x in this direction, but this is tensile in nature, this is compressive in nature, but the values are same, sigma y equal to sigma x magnitude wise. Okay. Then what I observe is that the failure or the yielding starts when sigma y equal to 200 by 2, that is 100 MPa. Okay, it is not giving you the same. So, you actually do not need to apply as much stress as you have applied in the case of uniaxial tension, only half of it will cause yielding. Okay. So, think about it, you are applying this load and then you are pushing in this direction. When you are applying the load, because of the Poisson's effect, you have lateral contraction, right. So, now you are pushing it by additional compressive force, and hence we can think, we can actually say that okay, because we are helping the system to yield by pushing it with the external force, and hence probably the sigma y has come down. Then what should happen? You are applying the load in this direction. Now, if you change the sense of your lateral load, instead of compressing it, if you pull it in the lateral direction, then what should happen? What do you expect to happen? Do you expect your yield strength to increase, to be higher than this case or not? Because here it is reducing, because you are pushing in the lateral direction. Now, instead of pushing, you are pulling in the lateral direction with the same value. Then do you expect to have your strength to be same or less or more. Are you able to see what I am trying to convey? So, normally we would expect it to increase because this guy is accelerating the process of yielding. That means at lower stress, this guy should postpone the yield. But it turns out that if you do the experiment, the yield strength is almost same as the uniaxial case. It is not significantly depending on the lateral load. Very small effect. Experimentally, it can be shown that. If you do the experiment, that's what you will observe. So, if you say that my yield strength, if you have a non-uniaxial loading in the material, to define failure is not obvious. Just by changing the direction of the loading, you are not able to make sense out of the nature of the failure, right? What stress leads to failure and so on. And that kind of an ambiguity is what is bringing in the need for defining a theory which can encompass all these variations in the loading scenarios, but still be able to give us a criterion for defining failure, irrespective of the type of loading that you have in the system. Okay? And that is why we need a failure theory. And these three things are one, and the third one is even more interesting. Sorry, fourth one. This fourth one, you have hydrostatic stress, which means in all the three directions, if you are applying compression in this direction, in the direction of y, xx and zz also you apply compression. That means the normal stress in all the three directions is the same, and that is what is called hydrostatic state of loading. And this is typically what you can generate by keeping a specimen underwater, right? If you keep it underwater, then the specimen is usually subjected to the hydrostatic state of compression. Let us say this material has same yield strength in tension and compression, hypothetically. Then it should yield at, should it yield or not? It should yield when sigma y becomes sigma naught or not. But it turns out that if you are applying hydrostatic loading, the material will never yield. You can see the material is continuing. So, just by prescribing hydrostatic stress, hydrostatic loading, the material will not yield at all. The plastic deformation cannot be imparted only by applying hydrostatic loading. And that is why you don't see the flow here. So, here your sigma naught, but this will never reach your sigma naught. You can keep on applying load. You can actually, in principle, you can go to any value, and the material will still not plastically deform. Okay? And this is very interesting. And then no failure theory, unless you have your failure theory taking into account of this physical phenomena, you will not be able to prescribe one theory which can describe the failure irrespective of the type of the load, right? So, that is what brings in the need for defining a failure theory. Okay? All right. When we are defining failure theories, at least in this class, as far as this class is concerned, we have certain assumptions. So, the first assumption, as far as static failure theories are concerned, we are assuming that there are no cracks present in the material. It's a very important assumption. Okay? The moment there is a crack, then you may have other issues. Okay? So, there are no cracks present in the material, and in this class, we are assuming the material to be isotropic and homogeneous. This is also very important. If your material is not homogeneous, your failure theory should be changing. The failure theory should give you different, as a function of space, you should be calculating your stress state, because that will be varying because your material itself is changing. Okay? And it should be, and we are assuming that the material to be isotropic, that means in any direction. So, we are not talking about yield strength in a particular direction, unlike for single crystal material. For single crystal material, you cannot make such an assumption, right? Can you or can you not? Isotropy. Are single crystal materials isotropic or not? Are you sure? Huh? We have spent a lot of time discussing single crystal materials are anisotropic by nature. Why? Polycrystalline materials are isotropic, many of them, unless there is some additional processing that is done, but otherwise in general polycrystalline materials are isotropic because averaging out of the orientations of all the grains, and eventually you will get an isotropic behavior. So, here we are essentially talking about failures in a polycrystalline material, in other words, because we are assuming isotropy. But in principle, you should also be able to derive these failure theories even for anisotropic materials. But in this class, we are restricting ourselves to isotropic materials. Okay? All right. So, how does the general form of failure theory look like? What should be the functional form? Okay? So, let us say the resistance of a material to yielding is called yield strength, that is something that we know, and that is for ductile materials. If you want to design brittle materials and the components made of brittle materials, then you need to consider ultimate strength as your failure criteria. So, the functional form of any failure theory for an isotropic material can be expressed like this: F, which is a function of sigma 1, sigma 2, sigma 3, where sigma 1, sigma 2, sigma 3 are principal stresses. That is important. Principal stresses at a point in a material. At a point, that is important. You do not have same stress everywhere, right? The stress state in a material may change from position to position. So, F of sigma 1, sigma 2, sigma 3 equal to sigma C. That is your material property. This sigma C is your material property, and for a ductile material, you will take that to be yield strength. For a brittle material, you will take that to be ultimate tensile strength. So, you should come up with a functional form. What is that functional form? Is something that will depend on which theory you want to. So, when we are talking about different failure theories, all these different failure theories in the end are different functional forms for this guy on the left hand side. If you have one functional form, you can call it as maximum normal stress theory. If you have another functional form, you call it as Tresca theory. If you have another functional form, von Mises theory. If you come up with your own functional form, your theory. Right? That's all. It is as simple as that. And there is a reason why different theories have come into place, because when there is no theory available, what people will do? They will try to come up with the simplest possible theory. So, we are talking about, historically we have been doing tension test, and then we were able to see at some load it is failing. So, what I can say is, okay, when my normal maximum principal stress reaches the yield strength of the material, that is when failure happens, right? That is actually maximum principal stress theory, right? And or maximum normal stress theory. Like that, different people have come up with different theories. And usually, the failure criterion is written in principal stress space. You are familiar with the concept of principal stress or not? All of you? How many of you are not familiar with the concept of principal stress? Good, everybody is familiar. So, if you know the stress state at a point in a material, then you can always find out a frame of reference which is oriented along the principal axis, such that in that frame your shear stresses will be 0, you will only have normal stresses. We will talk about it in a moment. If you did not understand whatever I have said just now, do not worry, we will talk about it in a moment. But you can express the stress state at a point, and then you can also find out the principal stresses. That means in a particular orientation. And if you are writing your functional form of the failure theory in principal stress space, that is why it is expressed in principal stress space. And typically it is written in principal stress space. Why is it written? There are certain reasons. A valid failure criterion, if you are coming up with a failure criterion, if it is a good failure criterion, then it should result in same outcome independent of the choice of your coordinate system. Your failure theory should not be depending on the choice of your coordinate system. It should be independent of your choice of coordinate system, and hence at a given point, if you know the stress state, you will always, your principal stress state is fixed, right? You know at particular orientation you will have your principal stresses. So, and hence if you take the principal stress space, that automatically satisfies this criterion, and hence failure criterions are usually written in principal stress space. But principal stress space is not the only choice, you can also use other invariants of the stress tensor. Okay? So, other invariants of the stress tensor can also be a possible candidates for writing your failure criterion. What do we mean by invariants? We will come to it in a moment, or maybe today or tomorrow. So, all the requirement is that it should be independent of the choice of your coordinate frame of reference. That is the only requirement, and that is the reason why principal frame of reference is considered. Or you can also consider your invariants of the stress tensor. You can write it in both ways. We will see there are failure theories which are written in terms of the invariants of the stress tensor. Okay? And when you are plotting your, so here this guy is a function, right? Is a function, and when you plot this function in principal stress space, it will be a surface, three-dimensional surface, and that surface is called failure surface. And if it is ductile material, then it is called yield surface. If it is a brittle material, then it will call that as fracture surface, but it is basically failure surface, the function that you have plotted in principal stress space. Okay? So, as I have already mentioned, different failure theories are basically different choices for the mathematical form of your function f, that is all. So, the moment you recognize that, you really do not have to worry about remembering different failure theories, you just remember the philosophy on which they have prescribed that failure theory. Then your functional form comes out automatically, you will be able to derive the functional form. Okay? And which functional form should I choose? Because we need to design stuff. So, what the best way to do it is, we choose the functional forms that actually match with the experiments better, whichever functional forms match with the experiments better. And please understand that just because a particular failure theory is representing experiments perfectly well for a given material, does not mean that that failure theory is going to be good for several other materials. So, this failure theory is only a mathematical abstraction or mathematical representation that we are seeking in order to represent the behavior. But your failure theory that you have prescribed might actually break down for some other cases. This is something that we should keep in mind. And people have done several experiments and they have tested their experimental data against these failure theories. And then they have seen that there are certain failure theories which seem to match with a large fraction of experimental data, and hence they said, okay, this probably is the right failure theory to be used for this set of materials, and so on. Okay? So, there are different failure theories as we have discussed. Maximum normal stress theory, it is also called Rankine theory because he prescribed this theory. This is simply when your maximum normal stress equal to yield strength of the material, that is when the material fails. So, your sigma xx is equal to sigma y or sigma 1 equal to sigma y, that is when failure happens. And then people said, oh no, I do not want to define my failure based on stress, I want to define my failure based on strain, and Savena defined based on strain, and hence maximum normal strain theory is named after. And some people said, no, I do not like stress or strain, these are tensorial quantities, I want to deal with scalars, and hence I will take something that is actually better than these two things, and he took strain energy. So, he said, I came up with another theory called total strain energy theory. And then von Mises came in and he said, okay, your total strain, I like your energy approach, but I do not agree with you completely. You want to take total strain energy into account, but I don't want to take total, I only want to take a little bit of it. And then comes von Mises theory. Not clear? And then Tresca came up with another theory, because we are talking about ductile materials. You guys are not even talking about the shear stress at all. Some of you are talking about stress, some of you are talking about strain, some of you are talking about energy. But we all know that plastic deformation is due to slip of atom planes, which is provided by the shear stress. So, I better define my failure theory based on the shear stress, and that is what is maximum shear stress. Right? So, you have different kinds of failure theories, and we need to look at how one would derive these failure theories. In this class, we will be focusing on these two failure theories, because these two guys seem to agree with experimental data available in the literature much better than other failure theories. So, they actually have seen other failure theories, and then they saw that there are some discrepancies, and then they want to fix. So, understanding the discrepancies from these failure theories, these people have come up with better failure theories. Okay. So, in this class, I have already defined what these failure theories are, or you can actually define, or you go back and read some textbooks, and then you will be able to write the statement of the failure theory. Each failure theory will have a statement, right. So, maximum normal strain theory statement could be what? When the maximum normal strain in the material at a given point reaches the strain corresponding to the yield of your uniaxial tension test, that is when failure happens, right. That is how they have defined. Similarly, total strain energy theory. So, you measure the strain energy in the material. When the strain energy is equal to yield strain energy, that means the area under the stress strain curve up to the yield point, that is when the failure happens. That makes sense to some extent, right. All right. And now we need to spend some time understanding principal stresses. And did we discuss the concept of tensor, stress tensor in this class? No. Okay. So, you know that stress is a second order tensor or not? Are you familiar with the concept of second order tensor? If you are not familiar, please let me know, I will spend some time. No. Okay. All right. So, what is a scalar? We are talking about physical quantities. You must have studied up to vectors in your +2, right? What is a scalar? A physical quantity which has only magnitude. What is a vector? A physical quantity which has magnitude and direction. So, a second order tensor is a quantity which has magnitude, direction and plane of action. We will talk about it in a moment. So, suppose if you are talking about stress, so let me draw it here. If you take an infinitesimal element, so let us say this is my x axis and that my y axis, that is my z axis. Okay. So, now if I have to represent my stress state, it is a stress state at a point. This is an infinitesimal volume, that means it is pretty small. We are only showing it as an infinitesimal volume, but it is actually stress state at a point, is represented by normal stress described as sigma x x. Okay. And this I am calling it as sigma xy, and this I am calling it as sigma xz. Similarly, on this plane you have one normal stress, that is sigma yy, and that will be sigma yx, and that will be sigma yz. Okay. Like that you can show your stress state on all the faces, right. And if you carefully observe, if you want to describe one element of this stress object, you are using how many indices? 2 indices. The first index, if you carefully observe, the first index in all these things represents the direction of the normal to the plane. What is the direction of the normal to the plane? X-axis. So, the first index represents the direction of the normal, and the second index represents the direction in which it is acting, right. So, this is called normal stress component because the direction of that particular stress component is in the direction of the normal itself. That is why it is called normal stress component. And this is shear because it is in the plane. So, the first one is x represents the normal. So, that means it is representing the plane. So, this is basically your plane of action, and the second index is representing the direction in which it is acting, sigma xy, and this is sigma xz, right. So, if you take velocity for instance, so velocity vector will have how many components in 3D? 3 components. So, if I say this is my velocity, or let us say displacement, u is my displacement, this tilde to represent that is the vector, I can write ux, uy, uz. Oops. So, this index represents what? The direction, right. Each index, so elements of your vector v, vector u are the projections of this vector on each of the coordinate frames, right. So, that basically represents your direction, component of the velocity displacement vector along x direction, y direction and z direction. But now, if you come to the stress, it is a second order tensor. In addition to the each and every element in this tensor is also required to be presented with its plane of action. That is why you need to use 2 indices. The first index represents the plane of action, second index represents the direction in which it is acting. Okay. So, in order to represent this stress in some mathematical form that is concise, we use matrix representation. Okay. So, that is why you would have written sigma as sigma xx, sigma xy, sigma xg, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma z. And this is what we call stress tensor. I put 2 tildes below to represent that it is a second order tensor, 1 tilde to represent that it is a first order tensor. So, a vector is a first order tensor. So, the order is nothing but the number of indices that are required to represent all the elements of that particular physical quantity. Okay. So, if you carefully observe, all the diagonal elements will have same index if both first and second indexes are same. That means it is a normal component. All the off diagonal components are your shear components. Okay. Now, if I multiply this stress tensor with, let us say 100, what is 100? The normal, the unit vector in the x direction, right. What will I get? Sigma xx, sigma xy, sigma x. So, what did I get? So, this is what is this? This is a tensor, second order tensor. What is this? This is a first order tensor, that is a vector. And what did we get? A vector. And this is what we call stress vector or traction vector. You probably heard of this traction vector. What is this telling us? If you have a stress tensor and if you are operating using this stress tensor, you are operating on a vector which is actually the normal to a plane, then what is it giving you? It is giving you the components of that stress tensor on that plane. That means the stress vector on that plane. Is that clear? So, now if I want to, if I have a stress tensor sigma, okay, and I am operating on a vector n, then I will get some vector t. This vector t I am calling as traction vector. This basically tells me on this plane what are the components of my stress tensor. Okay. So now I can write this as, this is what you call, this form of representation is called indicial notation, but don't worry about it. I don't want you to spend time on that, but all that I can write is that my traction vector on a plane whose normal is n can be obtained by operating this my stress tensor on that normal vector. Is that clear? Is there any ambiguity there? No, right? Good. Now, let us say, so what is the direction of this guy? So you have got, by operating this stress tensor onto this vector, you got the traction vector. What is the direction of the traction vector? That can be some direction, right? It can be any direction. What happens if the direction of that vector happens to be in the same direction as the normal to the plane? Is the question clear? You have obtained this vector, so you have got sigma times n equal to t, right? So this is the, so n is having certain direction, t will have some other direction. In general, it may have some other direction. What if that direction of t and n are the same? Which are, in other words, now in this case, under what conditions the direction of this guy will be same as this guy? When sigma xy and sigma xg are 0, when the shear stresses are 0, right? So if my direction of the resultant traction vector is in the same direction as my normal, then on that plane I will not have shear stresses, right? So such a plane is called what? Principal stress plane, right? So now mathematically I can describe, if that happens to be my principal stress plane, then I can write my T, that is the traction, is equal to I can describe my traction direction to be same as the direction of the normal, right? So I can write this lambda is a scalar. So I can write sigma times n, normally is t, but the magnitude can be different, but the direction is the same. Then I can write lambda times n. The direction is the same, then I can write lambda times n. Are you familiar with this form somewhere? Have you ever seen this kind of a form? It's an eigenvalue problem. So what will be this magnitude, by the way? See, if it is a unit vector in the same direction, then this will be your eigenvalue is fine, but from the stress tensor perspective, this is a normal stress component. That means that is your principal stress, isn't it? That means if you are given a stress tensor, if you find the eigenvalues of that stress tensor, the eigenvalues correspond to what? Principal stresses, and the eigenvectors correspond to principal directions. So that is how you are given a stress tensor, you can actually find out the eigenvalues, and then they will be your principal stresses, right? So that is how we have derived this here, A minus lambda I. So this is sigma minus lambda times I times n equal to 0, right? That is your eigenvalue problem. And then you will say that if this is your eigenvalue problem, then what should you solve? What should you do? If this is your eigenvalue problem, your n can be 0, but it is not, it's a trivial solution. What should be a non-trivial solution? This should be 0. Sigma minus lambda I, but that's a matrix, no? If that becomes 0, you are talking about it's a redundant solution. So this is possible for any generic n This is possible only when this matrix is singular, right? Because it's in the null space. So that means if it is singular, that means the determinant of this guy should be equal to 0. That is why we have to equate the determinant to be 0. When you write ax equal to lambda x, right? Several times we don't pay attention why. In order to solve this, we need to do a minus lambda equal to 0, determinant a minus lambda. The reason why we need to do that is because for a non-trivial solution, this should be singular, and if that has to be singular, then the determinant of that matrix should be equal, right? So with that, I stop, and then we'll meet in tomorrow's class and then build on. Okay.